It is, I know, stormy. Okay, so let's start by this. This word right here, graphing, is super important, and there's really a family of functions, and you know the linear family pretty well by now. In 6th grade, your teachers introduced you to something called proportional rate of change, all that stuff, right? And so then in 7th grade, Mr. Meeks picked up there, and he taught you y equals mx plus b, and you did slope, and then I kind of finished you off this year in algebra with linear functions. Like, I feel like you are so good with linear functions, you know how to graph, all that good stuff. But I want you to see now we're starting that same process again from the very beginning, except with quadratic functions. And then when you get to Algebra 2, they're going to finish up with quadratics. So let's start by just kind of looking at the parent function for something called linear. So do you remember when we first, I do a lot of review at the beginning of algebra because I'm like, hey, remember this from last year? And some of you say yes, and some of you say no. So I want you to write the word parent function. So have you ever heard that phrase before, anyone? Parent function? So a parent function means this is as simple as this linear function can get. Okay? And we're going to relate a lot to something called the table of values today. So I just want you to kind of look right here. And actually, I gave math tests out this weekend, and a couple 6th grade kids, well, they're 5th graders, they were trying to test out of 6th grade, came up to me, and it was like y equals x plus 3. Make a table of values. And they said, is that where you get to pick whatever x's you want, and then you put the x's in and you find the y? I went, yes, that is exactly what you do. So a table of values you can use for anything, for any function ever. I could give you y equals x cubed plus 3x plus 9 and say graph it. Well, if you make a table of values, you can graph it. Okay? So a good, I know it's thundery, so we're just going to work through it. So a good domain to use that we learned in Unit 6 is just the -2 all the way up to +2. It gives you a good idea of negatives, a couple positives, and 0. So this gives us a really good picture. So if what y equals x means in linear land means whatever x is, that's what y is. So then you basically just say, well, if x is -2, then so is y. If x is -1, if x is 1, and that actually is pretty simple. So I want to see what this does. So if I graph -2, -2, I'm here, -1, -1, 0, 0, 1, 1, and go, and so on. Yes. Hello. Hi. Yeah, absolutely, no problem. Bye. Drink. They need you in the office, okay? So then we took a ruler, we connected it, and now I want to show you something. Do you remember that line? It went through the origin, and the slope was 1. And it was like a really standard, like up 1 over 1, up 1 over 1. These were like just your regular stairs, right? Okay. So if you were on, and I use this example a lot, if you were on Who Wants to Be a Millionaire? I don't even know if that show is around anymore. And the $1 million question is, what is the slope and the y-intercept of the parent function? Most people would be like, I have no clue what the parent function even is. But do you know what the slope of a parent function is? Up 1 over 1, right? Because it's the number in front. And what is your y-intercept? When there's nothing after it. Do you remember that? Okay. So your y-intercept is 0. And your slope is up 1 over 1. Okay. So now I want to show you what the parent function of a quadratic equation looks like. The parent function of a quadratic equation looks like this. Boop. That's it. It's basically the y equals x, except it's not really just y equals x, it's y equals x squared. Quadratic, even though it sounds like the prefix for 4, right? It's actually quadratics are when your highest exponent is a 2. So guess what we're going to do? We're going to do the same thing. Go ahead and write parent function here. And we're going to make a table of values for this, and we're going to see what the parent function of a quadratic equation looks like. So let's use the same domain. I'm going to kind of fly through some of this calculation stuff. So if I say, actually, this is what this paper is for. So let's kind of move over here. All right? So let's say y equals x squared. Because I like this table, because it has a spot for you to show your work, which is a lot of times what causes kids problems. So let's do -2, -1, 0, 1, 2. All right? So this means that the y value will equal whatever the x value is squared. And so what is -2 times -2? It's positive 4, right? Let's do it again. Y is equal to whatever the x value is, and this time it's negative 1. And what's negative 1 times negative 1 times itself, right? This is easy. Take 0 and square it. It's 0 times 0. This, you don't have to write that out. Now, let's watch what's happening here. First of all, what do you notice right away? First it went down by 3, then it went down by 1. Is the rate of change constant? No. I know, because the only time a rate of change is constant is when it's linear. And I already told you it's not linear. It's going to be with curves this time, okay? So take 1 and square it, and you get positive 1. Take 2 and square it, and you get positive 4. So what do we notice about this? Does that look familiar? When did we see something like that? Remember where I said 0 is this, and then as you work outwards? Do you remember that from Unit 6? 6-1, graphing exponentials. Okay? So now I want you to take that piece of graph paper out that you have, and we're going to plot these points, and we're going to discover what a parent function for a quadratic equation looks like. Okay? So y equals x squared. So now, it's funny because after coming off of like slope, you have to remember how to plot a point. That was actually one of the questions on the 6th grade test out. Plot point, -8, 5. Well, you guys are so used to rise over run, but now when you plot points, you have to make sure you do left and right first. So let's plot -2, positive 4. Then let's plot -1, positive 1. The next point was 0, 0. The next point was positive 1, positive 1. And then positive 2, positive 4. Okay, and then we're going to stop right there. Because I told you that this is not a constant rate of change, you cannot have a straight line anywhere on your graphs. Do not make this a V, because it's not. Because if you go, it's going to kind of leave this out. So the first thing you're going to want to try to perfect is the art of making a perfect parabola. You start at the vertex and you just kind of curve it up like that. And you have to go a little bit out to get that, to hit all 3 points, really. So these are not V's at all. More like U's. Okay? So right now, what I'm looking at is the parent function y equals x squared, okay? End of the year, Miss Meeks usually will order like frogs, and you guys will do some dissecting of frogs, right? Does she talk about that yet? Where you sign up and you look inside of a frog, and you look at this, and you look at this part of it. So let's dissect this parabola right now. Maybe not as much fun, but... So I want you to look at all the parts of a parabola. I gave you a little sheet last week, didn't I? So I'm hoping to see what you remember about it. The first thing I'm going to always want you to point out with a parabola is what's the vertex. So go ahead and point to that right here. And so the vertex, I'm always going to ask you, is the vertex a maximum or a minimum? Maximum is like when your parents say, okay, you can have a sleepover, the maximum number of people you can have is 5. You can't have anywhere over 5. It has to be lower, right? So it's the highest. A minimum is the lowest. So is the vertex the highest point on this parabola or the lowest in this case? If I were to say what's the highest point, see those arrows? The highest point is infinity. But the lowest point is my vertex. So we're going to call the vertex, in this case, a minimum. And you know when you have a minimum? When your parabola opens upward. Because you can't have a parabola opening down and your vertex be the minimum. It just wouldn't make sense. Okay, so your parabola is either going to, this year at least, open up or down. When you get to Algebra 2, these things are going to fall on their side, and they're going to open sideways. That's an Algebra 2 thing. I don't do that. Okay, so far are we good? The vertex is a minimum when it opens up. Okay, the next thing I want you to take a look at is, what do you notice about these 2 points and these 2 points? Actually, before we do that, could you, and it kind of stinks, could you draw like a dotted line? And it's actually right on the y-axis though, right? So what is that dotted line called? Do you remember what I said about parabolas? They are what type of figures? Symmetrical, right? So they are symmetrical. Yes, good. So if I were to fold it on the y-axis, you know, this dot would fall right on top of that one, and so would this one to this one. So I want you to, as much as you can, draw a dotted line, and I want you to label that the axis of symmetry. Do you remember the little half sheet of paper I gave you that kind of has all this? Okay. One of the most important things I need you to know about the axis of symmetry is that it's a vertical line. Do not tell me the axis of symmetry is 3 or 1 or 7. What kind of a line is a vertical line? Do you remember when we had to graph that? Do you remember the y equals and the x equals? Do you remember when I said, well, a y equals is the horizontal because if you flip the y upside down, it kind of looks like a what? H. And the x equals starts out as a v. That's how you can make an x, is a v, right? So any x equals lines are vertical. So every time you write the axis of symmetry, and in this case, where does it touch? It's x equals and then a number. Okay? And in this case, the x is 0 because it's the y-axis. Okay? And it opens up. All right. So we have our parent function. I'm going to show you today 2 ways that we're going to change that parent function. All right? So let's go back to this. All right? And when I said y equals, let's see, I took the parent function. We have y equals x. What happened when I did that? Does anybody remember without having to make a table of values? Do you remember? This means whatever x is, yeah, it's going to be the opposite of it. So if I do I'm just going to kind of go quickly through this. This means take x, take the opposite of it, and that's what y is. So y is the opposite of x. So if x is negative 2, y is positive 2. If x is negative 1, then y is positive 1. Opposite of 0 is 0, right? And so what happened when I put that one little negative sign there? Boy, man, it changed everything. Because look what happened now. First of all, I'm always going to keep the parent function here. So if this is my parent function, my question to you today, because guess what you're going to have to do? You're going to have to write some sentences today in math. What? Sentences in math? Because you're going to be describing to me the changes. I'm going to say, hey guys, what does adding a negative in front of the quadratic parent function do to it? Tell me with words. It does this to it. So if I graph negative 2, negative, or positive 2, negative 1, positive 1, there's my 0, 0, 1, negative 1, 2, negative 2. What did adding a negative to the linear parent function do? Some people like to say it flipped it upside down. Did it kind of do that? Okay, what is a flip upside down? This was on the M step, I think. Was it a reflection over the x or the y-axis? Actually, this one could be argued it could be both, right? Because if I fold it on the y-axis, this pink line does that. What happens to it? Turns into the green line if I do it this way. So we're going to look at it as a reflection over the x. So guess what we're going to figure out now? What does that do? Hey, any crazy guesses here? Yeah. Awesome. He used 2 vocabulary words in his explanation. He says that's going to make it so that the vertex is a maximum now instead of a minimum. So let's go. Actually, I just want to point something out before we do this real quick. I want to show you something. I'm going to take this little thing, and what did I just make? A smiley face. Okay? So, because this is going to change tomorrow. What the first thing I want you to know is of the parent function, if you can find the vertex, your eyes, like your nose is the vertex, and I want you to picture your eyes being one up and one out in each direction. So it's going to be your up one, over one. Those are your eyes, okay? That's not going to be the case tomorrow. Your eyes tomorrow, we're going to be like super spread out. It's going to be like a weird, freakish looking person because your eyes might be all the way out here. And that's going to be when you have a stretch of the parabola. There's so much to learn about this. But I want you to know right now, if you could draw a little smiley face, if your nose is the vertex and your eyes are up one to the right and left, then you know that that's going to be your parent function. These 2 are just kind of bonus points. Bonus, if you can get, because if I were to say, how many points do you need to make a line? If I say make a line, here's a ruler. Can you make 1 point? And then, like, what do you do? Where do you put the next point, right? How many points do you need to make a line? 2. How many points do you need to make a parabola? 3. You need the vertex, you need the eyes and the nose. And then these you can always just kind of eyeball or guess. Okay, so let's graph this one. Y equals negative x squared. Okay, so let's plot those points. We did our table, or did we do our table yet? No, we didn't do the table yet. Okay, so let's do this. -2, -1, 0, 1, 2. Okay, so let's take, watch this, be careful. Put this, put x in there, and so what is x? -2. Stay with me for a second. Do this last. What is -2 squared? +4. And now what's the opposite of that? -4. What is -1? What's the opposite of -1 squared? Man, this sometimes can get so confusing. Find what -1 is squared first, then take the opposite of it. If you rely on a calculator to do this for you, it's gonna steer you wrong. We've had that happen before, right? Because it's all about whether you're using parentheses or not. This one doesn't even matter because the opposite of 0 is always just 0. Y is going to equal the opposite of 1 squared. Well, 1 squared is 1, and the opposite of 1 is -1, and then you can kind of already guess what you think. The opposite of 2 squared is -4. And so now let's plot that and see if reflecting with that negative does the same thing to quadratics as it does to linear. All right, so the first point I want to plot is -2, -4, which is and I'm not going to do this in pink. I'm going to do my parent function is always going to be in pink. I'm going to use the same color. And then this is going to give me 2, 4. Because my whole thing is, how does this function with a negative compare to it? So I'm going to do it in green, the shifts. So I have -2, -2, -4. Then I have -1, -1. Then I still have my 0, 0, right? And technically, once I have a couple points on the left, do I need to do the calculations for the right? No, because if it's symmetrical, if there's a point here, then there needs to be a point here. If there's a point 2 away from the x-axis or y-axis this way, then there needs to be one here. And then check our graph. It works. So did it do what we expected it to do? Did adding that little, and I'm color coding, negative green here, flip it upside down? Yes, it did. So if I were to say to you, describe with words and sentences and letters in math how putting a negative in front of the parent function changes the parent function, you're going to say it reflects it over the x-axis. Or you're going to say now it makes the vertex a maximum instead of a minimum. Okay, so go ahead and write that in your vertex. By the way, is your vertex the same in both? Your vertex is 0, 0 here, and it's 0, 0 here. It's just now a maximum. This is actually not that bad, is it? Because I got one more thing to show you, and then you're going to have literally 6 problems to practice. Okay, good so far? All right, so now let's go back over here, and we're going to do one more thing. If I took y equals pink for parent function, y equals x, but then I said, +3. So the little 5th grader who was in this classroom Saturday taking the test out knew that all they had to do was they got to pick whatever x values they wanted. They probably didn't choose negatives though, right? And then they had to put it here and then add 3 to it. So -2 plus 3 gave them 1. -1 plus 3 gave them 2. And technically, because I know this is linear, could I just keep going up by 1? Constant rate of change. 0 plus 3, 1 plus 3, 2 plus 3. And then, once again, if this is my parent function, through the origin, in pink, what does that green plus 3 do to a linear function? it just takes this, and let's plot it. -2, +1. -1, 2. 0, 3, 1, 4, 2, 5. And actually, I'm a little bit off, but. Okay, you see it in green. What does it do? It takes the parent function now we're getting ready to go to high school. You need some vocab in your back pocket. Somebody says it moves it. It shifts it. Shifts is better, okay? One thing that the 8th graders in Miss Everingham's class learned this year that you guys did not, because it is not part of an algebra curriculum, it's part of an 8th grade curriculum, is called translations. It's how do you move things around a coordinate plane. You can rotate them, you can reflect them. There's one called a translation. And look, a translation is like a slide. So if I were to take this highlighter, and it's here, and now I'm taking it and I just slid it. So a translation is a fancy word for a slide. So I want you to point to this, and it's a vertical translation. I slid it. That's all I did. Okay, and so I slid it up 3 units. So the +3 in linear moves the line up 3. So what do we think y equals x squared +3 is going to do? I don't know. I could take a wild guess, though. Let's use our table of values to kind of see if it does what we expect it to do. So let's take this, y equals x squared, and then add 3 to it. All right, let's do this one more time. This will be the last table we do. Because the last one I show you, you're going to already know where it's going to go without a table. I promise you. All right, let's take this -2. Let's square it, and then let's add 3 to it. So -2 squared is +4. +4 plus 3 is 7. Let's take this -1 and square it. Then add 3 to it. It's going to give me 4. 0. Technically, actually, watch. This is for the first time. It's not going to be 0, 0. Square 0, then add 3 to that. 0 plus 3 is 3. So at one point, somebody said, oh, 7 went down 4. Actually, it's not right. Constant. Take 1, square it, and add 3, and you get what? 4. Take 2, square it, add 3, and you get 7. Okay, so now, anybody have a guess? Take a wild guess at when I plot these points, what's it going to look like on my graph? Compared to the parent function in pink. It's going to, what did it do here? It was a vertical translation. I took that pink line and I slid it, right? So let's see if that happens here. So I'm just going to, real quick, I'm going to have you do this. Write your y equals x squared. There's your parent function. But then this +3 is going to be in green. I'm going to write my parent function real quick. I'm going to do my nose and my eyes. And then it's 2, 4 if you want to get that one extra set. And then I'm going to curve it a little bit. Because everything today is how does it compare to that pink function, the parent function. Well, now I'm going to pick up my green and I'm going to say, well, let's plot this first point, which was -2, +7. -2, +7 is right here. Then let's do -2, -1, sorry, +4. Then 0, 3. Then 1, 4. And 2, 7. Did it do what you expected it to do? Did it just take that parent function and push it up 3 units? So it was a vertical translation. It shifted up 3 units. Okay? If you want to use the word translation, that's great. Okay? So everything is compared to the parent function. There's your eyes and your nose, right? There's your nose and your 2 eyes. Here's your nose and your 2 eyes. Still just 1 unit apart. So my last question to you is, if I were to give you a graph that said y equals x squared negative x squared minus 1, would you need to make a table of values to graph that? Because what two things, how is the parent function going to change? Number one, it's going to do what? You could say it's going to open down, so the vertex will be a maximum. And where's the vertex going to go? It's going to shift down 1. Just for the heck of it. Just right here, do this. Take your eyes and your nose. Here's your parent function. 2, 4, negative 2, 4. Just right where you think this equation is going to land and what it's going to look like on your graph right now, before we even make a table of values. Because let's be honest, making a table of values is kind of a pain in the butt, isn't it? It's a lot of work. So the purpose is to not make a table of values right now. So the vertex is going to shift down 1. Did anybody start with the vertex there? And because of that negative, it's a maximum, which means everything needs to take place below it. And this time, my eyes and my nose are just upside down. Do you see the smiley still? Oh, it makes the parent function look like a sad one. This is the smiley for this. And then if you want to remember your 2, 4 and your, yeah, that one. Oh, no, it's actually not going to be that. Okay, that brings up a really good point. Let's talk about that. As long as you have these first set of points, you don't really need a second set and a third set and a fourth set. The more you go out, the more just exact detail you get. You can graph with the vertex and the 2 eyes. That's good enough. And so does this kind of show you how to graph parent compared to the parent function? I only taught you 2 things today. And here's my question to you. Were the 2 things that I introduced, this and this, did it do exactly what you expected it to do? Yep. Tomorrow, what I teach you is going to do not what you expect it to do. Okay? So you are going to